Hi, welcome back everyone to the class of Production Engineering 2. Today's topic is about the production logging and let's see what it is. We will discuss its details and implications and so on. The lecture is derived from the book of Michael J. Economites. It's a very nice book for production engineering. So those who like to work as a production engineer, they should keep this book with them and it will help them throughout their career. Well, first of all, in this picture, actually, it's not a one picture. We have multiple pictures. One, two, three, four. We have four different pictures here. And first of all, I give you 1 minute to look into all four pictures and find out what is the problem in these pictures. And then we will continue and I will explain to you what's the problem here. Okay, so now let's talk about these four pictures and let's see what's going on here. Well, in the first picture, we have a tubing casing pecker leaks. So, for example, we have the oil coming from here. Problem is here, this is leak. It's corrupt. So what is going on? The oil is going through here, and there's a casing leak, and it's going inside. So we are losing the production here. So oil is supposed to go inside, but it is not going here. It is losing here. So at surface, we think that the production is lost or production is reduced. Actually, there is production, but it is leaked. So this could be one issue. How to identify it? For example, in this reservoir, you have three wells. Okay, this is performing fine. This is performing fine. This is a problem. Okay, so if production is less than these two, so we are in the same reservoir, they all were supposed to be the same, but it's not performing well. So what we will do, we will look at it, what's the problem and how we identify it. As I said, that if we have a person standing here, this person is not going to go down. We cannot go inside. The what we can do, we can do some services here. Okay, so this is the first issue. Now in the second issue that you see here, we have water cement job. Okay, and this cement is not properly done. As you know, we do the casing to the cement, cementing to the casing. So this water, since the casing cementing job is not well done, so the water is channeled through it and water is coming with the oil. Now in this case, we assume at the surface that our water is coming from the reservoir. Our water is coming uh, our water is coming from this reservoir. Okay, but actually it is not coming from this reservoir. This is coming from the side through the cementing channel. So we have to identify again where this water is coming. Third could be the blast joints. For example, there's a leakage of tubing. Here you can see there's a leakage of tubing, and here you can see we have tip zone. We have oil coming from here. It's not going up, but it's going back from the above perforation. We have two perforations here, two perforations here. So oil production is not going to the surface. Actually, it is losing in low pressure zone here. And we assume at the surface that production is lost because the reservoir is not performing well. But reservoir is performing well, but production is lost through the plumbing system. So these are the issues, the damage issue. Not only them, there are some more issues. For example, what if this perforation is blocked here? Okay, they don't perform well. So this could be another reason. Or what if the tubing here, okay, is leak and this oil is going from here to inside. So could be any issue here. What if there is a wax inside? There is a lot of wax and the road is blocked and the tubing is blocked inside. So in this case, so these are the issues. But how to identify them? Well, in order to identify them, we need the production logging service. So production logging service is, as you studied from the well logs, is a case tool service. Usually we use the gamma ray logs and some other equipments, and we have number of objectives that we achieve here. We look for the cement monitoring. We check if there is any leakage. As I said, cement monitoring is important because water can come from that zone, gas can come from cement zone, or the oil can be lost inside. through these channels. So we have to monitor the cement. Corrosion, because leakage can happen in casing, tubings. We have to monitor the corrosion. Fluid contacts, maybe water level is rising, gas level is going down, so we don't know what's going on. We have to monitor the fluid contacts and saturations. As I said, perforations can be blocked, and these are the only communication way through which the reservoir communicates with the plumbing system. So we have to look for the perforations. The perforations are working fine or not working fine. And as I said, the packers are leaked or not leaked. Packers are properly installed or not. So we have to look at the packers. So these are the jobs that needs to be done, and we use the PLT production logging service in order to find the performance of the well. Okay, but the question is that this PLT is not used only as a alone. It has to be done with two other things. So the production logging is not the well diagnosis. I mean, it should not be just you put like a thermometer you're putting and checking with the temperature. Actually, you should have an objective. What exactly you are checking with the production log tools? As I said, there are a number of integrity issues. So what exactly you are checking? Are you checking the channeling? Are you checking the pecker? So when you do the PLT, it should not be applied without an objective. Prepare your objective and then apply it and look at it, and it will help you. Plus, it should not be used alone. You should always accomplish it with the help of the well test analysis, and especially the build-up test, or and look at the production history, especially nearby wells, how much water they are producing, oil they are producing, or gas they are producing. Then it will help you to identify what PLT is doing. So this is the diagram of the PLT. You see we have number of equipments. So we have exactly 13 equipments. Look at 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. 12 equipments, for example. So now majorly you see that we have here the thermometer, okay, manometer, we have a gradiometer, we have the spinner to check the velocity, we check the flow, we look at the saturation using the gamma ray or the leakages. We have the uh, you can see here we have a casing color law, look at the integrity of the casing. We have here so we have number of equipments here. We monitor pressure, temperature, flow meter, velocity, leakages. It has camera also nowadays in the modern tool. I will show you all of them. So in this one, it has many applications, but we look at them. There are 5 major applications that we look at them. And you see that where here we have, first of all, we diagnose the production problem. We look at it, how much, if the production is lost or reduced, why. So we do the PLT, we monitor it. We monitor the cement placement, if the cement job is done fine or not, cement is channeled or not. So we do monitor the cement. We look at the monitor the corrosion, if there is any issue of corrosion or not. Saturation, exactly where is oil water contact, gas water contact, or these one, or if there is a problem with the tubing or is a packer leakage, so we go for recompletion. So we have these 5 major applications, and we will discuss one by one all of them. First, look at it. We look at the diagnose production problems and allocate zone. In order to diagnose a production problem, what do you mean by the diagnosing the production problems? Okay. First, this is the question. What do you mean by diagnose production problems? So just prepare the question answer in your mind, and what does it mean? Okay, it simply means that uh, if your well has producing extra water, if the well is producing extra gas, or if the oil production is reduced, or if the gas production is reduced, what I mean, especially related with the production, why the water production is rising? Is it, I mean, what kind of problem it is? Maybe water is coming through behind the cementing. So, or maybe oil is lost because of the blocked or plugged perforation. So what is the issue? So these kind of diagnosis needs the temperature surveys, mechanical flow meters, borehole density surveys, and basket flow meters. These are the equipments that are needed for the one. And what they do, they check the fluid velocity or fluid type. Okay. And definitely these tools are run to determine if there's a production problem, there's water problem, completion problem. But definitely this is not used alone. It helps. It is used with the help of well test and other one. So now I will show you some video of production logs. and then we continue.
Swift, accurate downhole measurement is crucial in order to maximize cost-effective hydrocarbon abstraction. In complicated flow regimes, particularly within deviated and horizontal wells, conventional production logging tools are often inadequate. GE has developed innovative production offering the most robust picture of your well's.
Look at this production logging tool. This is production while drilling, production logging while drilling. So they drill, now they cement it, and then they use the logging in order to check the cement integrity, as I say. See the perforations done. Yeah, so the next problem we are discussing here is we monitor the cement. We have to monitor the cement, exactly where the cement went. Is it at the right place or the wrong place? And as you know, all the casings are cemented. And whether if we have the dual completion zone, whether this cement is providing zonal isolation or not. So this is the issue. Otherwise, the oil may be lost inside through the cement channels, or we have to solve this. The log used to indicate cement top includes temperature logs. Okay, we look at the hydration heating, temperature logs are used, gamma ray log is used, it looks at behind pipe density, and regular bond log is used, okay, to check the as you see that acoustic deadening. Okay, zonal isolation is needed because we don't want fluid to go from one place to another place, and we at the surface may be thinking that what is the real problem. So we have to diagnose it, what is the issue here. So what are the tools that are used? Cement bond logs, temperature log, noise, radioactive tracers, and so on. So we have to monitor the corrosion because corrosion is the issue. It can cause the leakages, and then if the leakages occur, the oil will be lost there, and we have to. So these are the tools that are used to find out the the corrosion and zonal isolation in this case. So these are some cement bond logs, and we have to look at it like where the cement went. Okay, this is the issue here. And cement usually is done to support the casing to prevent the fluid from leaking to the surface. So we monitor using the cement log. So we have the temperature log. I will show you the temperature log and its working mechanism, noise log, tracer log, and neutron logs. And when we talk about the equipments, we will talk about them and so on. Okay. Also, we have the caliper tool. It tells the inside diameter of the tubing string, and it tells us that if there is any issue with the uh, inside leakages or any diameter is reduced of the tubing or not. Okay, or how is the situation inside the surface? So it tells us the situation of the corrosion in this case. and electromagnetic device. Or nowadays we have camera also. Camera tells us there are leakages or not at the same time. Okay. Then we have monitored the fluid contacts, especially the neutron logs. These neutron logs are used to monitor pulse neutron logs, the various spectral logs. They are used to look at the situation of the uh, fluid contact. Where is oil water contact? Where is gas water contact? And usually the Schlumberger is very good for logging service and so on. So now we talk about these equipments and the details of the PLT equipments. As you see that we have number of equipments here. Uh, Casing color log, telemetry, gamma, quartz, gamma ray, tracer, telemetry, and thermometer, manometer, the gradiometer, full bore spinner or flowmeter. Now I will show you these components one by one and we talk about their functions, so on. These are the major components as we discussed. And first of all, let's look at it, the wireless telemetry. This is the equipment, a communication channel. Okay, the purpose is to whatever data is coming from the well log, here it is processed and sent to the surface using this tool, the wireline telemetry. So it's a two-way serial communication between the surface equipment and the PLT tool. So this is, as you see at the top, PLT. Usually, this is the telemetry interface here. Top of the equipment here. The purpose is to record all the data, keep it there, as well as communicate at the surface through the wireline, because this is connected through the wireline using this wireline here. You can see it's connected through here, and we have to look at it for the surface that this is the one. Then after this wireline telemetry, we have the casing color log, and it tells us the metallic mass changes inside the bore. So it tells us that if tubing the ID has changed or not, or it is the same. Of course, we change the depth, the ID of the tubing string related with the depth. Okay, and it also tells us where exactly the perforation is, where exactly the pickers are, nipples are, or other mechanical components. So this is the casing color log, and I will show you in a video now this log. Determines. Temperature tool. Okay, and it tells us the temperature wherever it crosses. It tells us the temperature, what's going on there, and it tells us the cement placement based on the temperature. It finds the low circulation zone. It finds the exit and entry point. It also helps us locating where is oil water contact, gas water contact, because the oil and gas, they have different temperatures and so on. And I will show you now the temperature.
Integrated video caliper tool, which enables real-time well diagnosis. By combining the best-in-class qualitative and quantitative sensors in a single tool string, IVC provides a unique view of well integrity issues, so that you rig down understanding the issues in seconds. The IVC features a 24-arm multi-finger caliper with 3mm vertical resolution and on-site reporting software, delivering real-time accentualization and 3D plotting. The tool string is run in the well, with the downview camera operating to get an overview of the well condition and hardware. The caliper is then logged up, with results displayed in real time. In this example, the on-site engineer inspects the log for any potential integrity issues or anomalies, using the 3D rotational facility and cross-sectional plotting. The caliper clearly indicates a feature, but given that this is a P110 casing, a split might be thought unlikely. With the ability to drop down and inspect the feature in detail using the HD E-line camera, there is no doubt about the issue. The HD E-line camera provides a level of detail unachievable from a multi-finger caliper. With both down-view and side-view cameras providing full-colour video, features such as corrosion, wear, deformation, splits or holes can be inspected in detail. The quantitative and qualitative measurements provide an ideal complement to each other. The video also shows how fluid flow is easily seen with HD E-line, as bubbles can be seen leaving the wellbore through the casing split. Based on the combination of caliper and video in a single tool string, the customer can rig down, sure of what the issues in the well are, having spent the minimum amount of rig time doing so. IVC changes the way well diagnosis is performed. In addition, on-site interpretation is backed up by EV's dedicated interpretation centre in Calgary, staffed by experienced log analysts who run.
Then we have the fluid capacitance tools, and this tool helps us to distinguish between water and hydrocarbon by measuring the dielectric constant water. So this tool tells us exactly where is hydrocarbon and where is water based on the difference in their dielectric constant. So let's look at it how it works. Okay, after this fluid capacitance tool, we have this is the fluid capacitance tool. The job is to find out how much is the water and how much is the hydrocarbon. And so it takes us some liquid and it tells us the analysis at the surface using the wireless telemetry how much water and oil is coming inside it. Then we have the flow meter spinner, and this tells us the velocity, exactly what is coming out, and this is the flow meter. Flow meter is run below a telemetry section which supplies power to the tool. So one purpose is works like a wind energy. The propeller is rotated and it gives energy to the telemetry to transfer the data to the surface. So you can say it provides electric current using this flow meter. This is one job. Secondly, tells us the velocity inside, and it is used to help the production profile, injection profile, any leakages. All these electric things are done using this fluid spinner. Okay. Then we have the gauge pressure. It tells us exactly at what depth what is the pressure. And this is also used in the pressure buildup analysis when we have to get the bottom hole pressure continuously versus rate. So gauge pressure is used to obtain the pressure.
Gamma ray log is a measurement of the natural radioactivity of the formation. Because radioactive elements tend to be concentrated in shales, the gamma ray normally reflects the shale content of the formations. The gamma ray log is scaled in gamma API units of radioactivity, with high readings causing a deflection of the curve to the right, and low radioactivity causing a deflection to the left. Thus, high readings indicate shale, and low readings indicate clean, non-shaly formations, like sandstone, limestone, and dolomite. However, a clean shale-free sandstone may also produce a high gamma ray response if the sandstone contains micas, potassium feldspars, glauconite, or uranium-rich formation waters. Thus, the presence of a clean sandstone can be overlooked if it contains one of these radioactive contaminants. If radioactive contamination is suspected, a type of log called a gamma-ray spectral log can be run that breaks the natural radioactivity of a formation in
respond to the bulk flow rate, even in multi-phase flow. A turbine or spinner rotates as a function of the rate at which fluids flow past it. If the spinner response in a static fluid is plotted in revolutions per second for several logging speeds, both up and down, the relationship is linear. The lines do not, however, go through the origin. The cause of this shift is the viscosity of the fluid. Greater viscosity tends to cause a greater shift. When the spinner encounters an upflow, as would be expected in a producing well, the effect is to shift the response curve of the tool to the left by an amount equal to the upflow velocity.
The flow velocities measured are those seen by the spinner turbine blades. If the spinner is centralized, and it should be for best results, it has sampled the flow from the center of the well bore, but too high, which is not representative. As a result, a flow profile correction factor must be used, typically 0.83.
To compute the bulk flow rate in barrels per day or cubic meters per day, one must multiply by the proper conversion factor and wellbore ID squared. The cumulative bulk flow for different entry points is determined by difference. For multi-phase flow, Once the bulk flow rate and holdup of the phases are measured, the slippage velocity of the light phase through the heavy phase must be determined. The relationship for slippage velocity is a function of holdup and fluid density difference. For example, for an oil density of 0.7 grams per cubic centimeter, a water density of 1.0 grams per cc, and a water holdup of 0.70, the slippage velocity per minute with a gas-liquid system, a slippage velocity of 60 feet per minute, 18.3 meters per minute, can be.
Okay, so now this was the production logging tool, their applications and the parts of equipment that it has. Now we talk about their example, and we look at the case studies that how production logging helped us to identify the problem of the well. So this we will discuss in the next video. So stay tuned and see you in the next video.